Okay, so previously we already talked about some different thermodynamic analysis of Otto cycle by using two different approaches. So we already discussed whether it will be a variable specific heat and whether it will be a constant specific heat. But whenever we have to talk about the spark ignition engine, we cannot deal all the thermodynamic analysis by using the assumption that there will be isentropic process, because isentropic expansion and isentropic compression means there will be no heat involved in it. Okay, so there will be an assumption that the entropy is constant throughout this compression and expansion process. However, when we are talking about the actual cycle, which is your Otto cycle or actual spark ignition engine, it cannot be isentropic process. Okay, so we will see that what these processes are called when it will be not an actual process. So in order to just say it will be not an actual it will not be an ideal process, so we will define a term polytropic process rather than isentropic process. Okay, so this is another term. I think you all are very much familiar with it because this is from your thermodynamic 1 book. Okay, so this is mentioned in your chapter number 4 as well. So what happens over there, because not all processes are basic type, that is called iso. It means that entropy is not always constant in your actual cycle, or it can be approximated by one of the basic processes type. Okay, and in order to define your actual process, what we have to do is, previously you already know that we use PV K is equal to constant for your isentropic processes. Okay, so any isentropic process we can represent with this equation, which is your K, which is the specific heat ratio. But here what we have to do is, in order to deal with the actual cycle, we just delete this K and replace it with N, and that N is called the polytropic exponent N, or it can be called as a polytropic index as well. Okay, so what is the meaning of this N? So this N has different meanings. So first thing is, if N value is 0, this is called a isobaric process. So if you can just put N value as 0, you can find that you will find a pressure constant over there. If it turns to be limited, infinity, it turns out to be a constant volume process. If your N value is equal to K, okay, so which is our previous case, it turns out to be an isentropic process, which we already see in the previous lecture. So if N is equal to K, it is an isentropic, adiabatic isentropic process. It means that your heat transfer is 0 in that process. Only work is produced over there. Okay. And then N is equal to 1, it is isothermal process. So when we have to assume that it is a polytropic process, in order to just turn out to be more accurate comparison with the actual cycle, we say that N value is any value. Okay, so it will be not a 1. Okay, it is not equal to 1, and if it is not equal to 1, we can define the boundary work. So boundary work is in between. For example, these are two states point. So boundary work you have to define with M is your mass fraction of your air or any working fluid over there. R is the gas constant over there. T2 is your final temperature. T1 is your initial temperature. It can be any state. And 1 minus N. This N is mentioned in your problem statement by the term, either it will be mentioned it is a polytropic exponent, or either it will be mentioned it is a polytropic index. However, if N value is equal to K, it is the same thing which we already discussed in the isotropic process. Now question is where this relation come from and how to do the verification of this WB. So for this you have to just follow your chapter number 4. I will just quickly give you an idea over there. So here this is your chapter number 4, page number 171. It is written over there, polytropic process. So you have to go through this by your own if you need to find out that how this verification or how this relation come from for your boundary work. So here it is the written over there. If N is not equal to 1, it's turned out to be this relation. If N is equal to 1, it's turned out to be this relation. Okay, so this comes from your mathematics knowledge. So I will suggest you have to go through it by your own after this lecture. So we directly use this relation in order to do the thermodynamic analysis of the polytropic process. Okay, so you will get the clear idea when we solve the problem. So we will, in the next slide, we will going to solve one problem so that you will get the understanding of it. Okay, so now this is the problem which is related to your polytropic process. So here it is mentioned over there, the compression ratio of an air standard Otto cycle is 9.5. So your R value is given over there. Prior to the isentropic compression process. Okay, so here it is mentioned that your compression process is isentropic. Okay, so here it is clearly defined that isentropic compression process, the air is at 100 kilopascal and 35 degrees C. So it's mean your pressure at point number one and temperature at point number one is given to you. And 600 centimeter cube. It's mean the volume at one is also given in the question V1. The temperature at the end of polytropic expansion process is 800 Kelvin. Okay, so now here it is defined that your expansion process happening polytropically. So it's mean there we have to use the value of N rather than you have to use the value of K. If it is mentioned in the question, your compression process is also polytropic process. So again, you have to use the same procedure which we discussed in this example for both of the cases. But here it is mentioned isentropic compression. So you have to use a similar procedure for compression process, which we already discussed in the previous lecture as well. But for polytropic expansion process, the method is different. Okay, so using the specific heat value at room temperature, so it's mean it is a constant specific heat value problem. Part A is the highest temperature and pressure in the cycle. So it's mean your T1 and pressure 1, you have pressure T3 and P3 you have to find. B part is the amount of heat transfer in kilojoule. Okay, so here it is mentioned kilojoule. So do not go for the kilojoule per kg, which we already did in the previous examples as well. The thermal efficiency you have to find and the mean effective pressure. So there are four parts of this example. So let's see how to solve this type of problem when there will be a polytropic expansion process. Okay, starting from the TS diagram for this type of cycle. So again, you already know that you have to start from your PV diagram, okay, and you have to build it by yourself. So from 1 to 2, there will be a compression process. From 2 to 3, there will be a constant volume heat addition process. Okay, so 3 to 4 is your expansion process over there, and 4 to 1 is your heat rejection process. This is your Q out, Q2. Okay, so now previously we see that we have to define that it is an isentropic compression process over there, or we just write isentropic expansion process between 3 to 4. But whenever it's in the problem, it is mentioned that it is a polytropic process for your expansion one. So you just need to write polytropic over there, and the curve is the same one. Okay, so there will be no, and you just have to write expansion process from 3 to 4. Okay, so now another thing which we have to add is whenever there will be a polytropic process. So previously we see that for isentropic process it is an adiabatic process, so Q is equal to 0. But polytropic process is not an adiabatic process. It's mean that there will be another Q involved in it, which is your Q in. Okay, so that come from your expansion process as well. So here we have to deal with the work as well and the Q as well. So we'll see how to solve that type of process for 3 to 4. Okay, so now we will start from the process 1 to 2 in order to find your maximum temperature T3 and P3. Okay, so the temperature at T1 is given, compression ratio is given. So you already know that for isentropic process, which is your 1 to 2, the relation that is valid is T2 over T1 is equal to V2 K minus 1. Okay, so for isentropic, same value for K you have to use over there. If it is mentioned it is a polytropic, then the story is different. Okay, so now T2 is equal to, so T1 is given over there 308, and this is I think your problem 9-38 from your book. Okay, so you have to follow from there. And K minus 1, 1 minus 4 minus 1 is equal to 0.4. So just by solving you will get 757.9 Kelvin of your temperature at point number 2. Okay, so now again you have to apply another relation in order to find the pressure, which we already know that your relation P1 V1 PV over T is equal to constant is valid for your all the processes. So P2 V2 over T2 is equal to P1 V1 over T1. So from here you can easily find P2 is equal to T2 over T1 and 2, and this is your compression ratio because it is the ratio of maximum volume over minimum volume. This is you already find in previous part. T2, T1 is mentioned in your question, T1 is also mentioned in your question because your initial pressure and temperature is given over there. So you can just plug in the value 9.5, 757.9, 308 Kelvin for your T1 and the pressure of 100 kilopascal for your P1. And by just plugging all the value, and you can just solve it, 2338 kilopascal for your P2 value. Okay, so this is your pressure 2. So you can just note it down, then I will move forward. So here it is a clear TS diagram over there. So just you have to write polytropic over there, and here there will be another Q. Okay, so now dealing with the process 3 to 4. Okay, so which is your polytropic process. So for polytropic process, we already know that your boundary work. So between 3 to 4, W3 to 4 is equal to MR, your T4 minus T3, and 1 minus your polytropic index. Okay, and it is mentioned in your question polytropic index value, which is N is equal to 1.35. So now the question is you have to find M. R is mentioned from your thermodynamic table. You can find it value in your A2 table. So T4 you have to okay, so T4 I think is given in your question because it is mentioned at end of the polytropic expansion process the temperature is 800 Kelvin. Okay, so T3 you have to find, and this N is mentioned in your question as well. Okay, so now coming towards your T3. So first T3. Okay, so as it is a polytropic expansion process, so the relation that is valid is T3 over T4 is equal to 3. Now it is N minus 1. Okay, so previously we used K minus 1. So here we have to just replace it with the polytropic exponent. Okay, so T3 is equal to, so T4 is available from problem statement, and V4 over V3 is your again compression ratio, which is equal to 9.5, and now N minus 1, which is 1.35 minus 1 is equal to 0.35, and by just solving it you will get the value of 1759 of Kelvin. Okay, so T3 is known to us. Now we have to find M, which is your mass of your working fluid. So M is equal to P1 V1 over RT1. Okay, so P1 is equal to 100 kilopascal from your problem statement. V1 is also mentioned in your question that your volume at the start is 0.6 meter cube, which is mentioned over there 600 in your problem statement. Okay, so R value is 0.287 is the constant, and then T1 is equal to 0.8 Kelvin. So by just solving it, you will get the value of 6.788 into 10 raised to power minus 4 kg. So here your M value is known to you. So now if I just plug in all the value in this equation, you can say your equation number 1, and you will get W34, which is the work associated with your polytropic expansion process. Okay, so you can just note it down, then we will move on towards the next step. Okay, so now W34 is equal to, the M value is 6.788 into 10 raised to power minus 4. The R value is 0.287. T4 value is 800 from your problem statement. T3 value we just find out, and 1759, and 1 minus 1.35 in your denominator, and by just solving you will get 0.5338 kilojoule of your W34. So this is your boundary work for your polytropic expansion process. Okay, so now what we have to do is we also have to find the Q that is from associated with your polytropic process. So how to find that Q, which is Q34? Okay, so we have to apply the energy balance equation for your process 3 to 4. So as you know that E in is equal to E out is equal to change in energy of your system. Okay, so here for this one you know that this is Q34. So now here Q34 is also there, and your W34 is also there, and this is equal to M CV T4 minus T3. Okay, so this relation we already know that this is equal to change in internal energy. Okay, so this come from your previous lecture. Okay, so now Q34 is equal to MCV T4 minus T3 plus W34. So W34 are already we find in the previous step. So this is the W34. T4 is already known to us, and T3 we already find out in the previous part. So CV value, either you can remember it for your A value, or you can find it in table A2, or M value we already find in the previous step, which is 6.788 into 10 raised to power minus 4. So now you can easily find your Q34, which is the heat associated with your polytropic process. So you can just plug in all the values: 6.788, 10 raised to power minus 4. CV value is 0.718, T4 value is 800, T3 value is 1759 Kelvin, plus W34 0.5338. Okay, so by just solving this, we will get Q34 is equal to 0.0664 kilojoule. Okay, so this is your heat that is added to the air during the expansion process. Okay, so we will use that heat in order to find your total Q in your system. Okay, because in your polytropic process, so here there will be Q, so your total Q in is equal to Q between 3 to 2, or you can say 2 to 3, plus Q 3 to 4. Okay, so that's why we need Q in order to find your efficiency as well. Okay, so this is your part number A. Now we will move towards part number B, which is to find your Q in, total Q in. And also we already find the temperature at 3, so we also have to find pressure at 3 as well, because we have to find the maximum pressure and temperature. Okay, so for process 2 to 3, we have to find the pressure at number 3. So again, the equation that is valid is P3 V3 over T3 is equal to P2 V2 over T2. Okay, so as you know that your V3 is equal to V2 from your PV diagram, so this becomes already cancelled, and P3 is equal to T3 over T2 into P2. Okay, so now all these values are known to you, because T3 is given to us, T and T2 is given to us, and pressure at 2 we already find in your part number A, okay, which is 2338 kilopascal. So P3 is equal to 1759 Kelvin, 757.9 Kelvin T2 value, and T2 value is 2338 kilopascal, and you can just solve it and you will get 5426 Pascal for your T3. So this is your first part, which is to find T3 and T3. So T3 we already know, and P3 we just find out. Okay, so now coming towards the Q23, because we have to find the heat associated with your process 2 to 3, which is your constant volume heat addition. So for constant volume heat addition process, the relation that is valid whenever you have to use assumption that is constant specific heat, so mCV into T 3 minus T2. Okay, so now M is known to us because we already find this value 6.788 in 10 raised to power minus 4. CV value come from your table A2, and T3 value 1759 Kelvin, and T2 value is 757.9 Kelvin. So by just solving it, you will get the value of Q23. So its value is 0.4879 kilojoule. Okay, and keep it, remember it is mentioned over there, you have to find in kilojoules, so that's why we have to go for the kilojoule. If it is not mentioned, then we just keep this part over there and we can find in kilojoule per kg. Okay, so this is your Q23, and now we can easily find the total Q in. So Q in is equal to Q23 plus Q34. You can just write it down, then I will move towards the next part. so now the Q in for your Otto cycle is equal to Q23 plus Q34 when there will be a polytropic expansion process. So if it is mentioned it is a polytropic compression process as well, so there will be another heat which is equal to you have to add Q12 also. Okay, so this is the difference. So here it will be only mentioned it is the expansion process which is polytropic, so that's why we just have to deal with two heat additions. Okay, so now we will see that
सर ये पॉइंट जरा दोबारा बता दें.
okay, so I have just mentioned over there. So whenever there will be a polytropic process, there will be a heat addition over there. So here in this question, it is mentioned it is the isentropic compression process. So that's why we do not have to deal with the heat for process 1 to 2 over there as well. So if it is mentioned in your question, it is the polytropic compression as well. So then you have to add three heats over there. So we will see that whenever it comes from the problem, how to deal with that problem as well. So here it is mentioned, it will be a expansion process, which is polytropic. So that's why we have to just add two heats over there. Okay. So we will see whenever we have to solve that problem, which deal with the two processes, that is compression process and expansion process as well on a polytropically. So how to solve that type of problem. Okay, so now Q23 is 0.4. Okay, so what is the value of 0.4879 plus 0.0664? So Qn is equal to 0.55543 kilojoule of your Q in. Okay, so this is your part number B, and now moving towards your part number C. So we have to find the efficiency of your cycle. So in order to find the efficiency, we already know we need W net, and W net is equal to Q in minus Q out. So Q in is known to us, and Q out we have to find out. Okay, and Q out you can easily find whenever it will be a constant volume heat rejection. So the relation that is valid for your constant specific heat assumption MCV T4 minus T1 between your process 4 to 1. So here M is known to you, 6.788 into 10 raised to power minus 4. CV value is 0.718. T4 value is 800. It is mentioned in your question that end of the expansion polytropic expansion process, it is 800 Kelvin and 308 Kelvin of your T1. So by just solving it, you will get 0.2398 kilojoule of your Q out. So now both Q in and Q out are known to us, so we can easily find W net over there. So W net is equal to 0.55543, so which is Q in, and minus 0.2398, and you can just solve it and you will get 0.3145 of your kilojoule W net. Okay, so this is your W net, and from this W net we can easily find the efficiency as well. You can write it down, then we will move towards the next step. Okay, so efficiency is equal to W net over Q in. So W net we already know, 0.3145, and Q in 0.5543. Okay, so now you can just solve it and you will get 56.7% of your efficiency. And keep it, remember over there that we already developed one equation which is 1 minus 1 over R K minus 1. Okay, so this equation is not valid for your polytropic expansion process whenever there will be a polytropic expansion process mentioned in your question, because this equation is developed for two isentropic processes. So that's why you cannot just put the value of R and you can just deal with this type of equation. Okay, so now coming towards your part number D. So part number D is mean effective pressure. So W net, we already know from your previous lecture as well, W net is equal to V1 1 minus 1 over expansion ratio. So previously we find the specific volume at 1, but here we can know that this value is given in your question as well, and that your volume at the initial point is at the start of your compression is 600 centimeter cube, I think. So you can just simply put the value. W net is known to you, which is 0.3145. This value is 0.006 meter cube, and this is 1 minus 1 over 9.5, which is your expansion ratio. And by just solving it, you will get the mean effective pressure as 586 kilopascal. Okay, so this is the solution for your problem whenever there will be a polytropic process involved in it. So if you have any question, you can ask me, and otherwise we can proceed further.
सर प्रॉब्लम में वॉल्यूम दिया हुआ था कि स्पेसिफिक वॉल्यूम दिया हुआ था?
आपको वॉल्यूम भी अगर दिया हुआ हो तो आप उससे वॉल्यूम, आपका स्पेसिफिक वॉल्यूम क्या होता है आपके पास? वॉल्यूम ओवर मीटर क्यूब पर केजी होता है, तो आप उसको कन्वर्ट कर सकते हैं ना इसमें।
यस सर।
समझ आ गई आपको? ये देखें ना, पहले क्या हमारे पास था यहाँ पे, पिछली प्रॉब्लम में W डॉट नेट था ना, विच इज किलो जॉल पर केजी. Here it is W net, it is kilojoule. Okay, so then we can just simply write V1 over there. If it is kilojoule per kg, then we use specific volume at 1.
यस ठीक है।
ठीक है. Okay, so now moving towards the question which you have to solve. It is also the same question, only the data is different over there. So and the exponent value is different, so you just have to do it by yourself, again by using the specific heat value at room temperature. So the compression ratio is given, pressure 1, temperature 1, volume 1 given over there. Same, the end of polytropic expansion process, 900 Kelvin is your temperature. Polytropic exponent n is equal to 1.2. So you have to find highest temperature and pressure in the cycle, the amount of heat transfer in the kilojoule, thermal efficiency, and mean effective pressure. So this is the problem, and you will get the time till night.